All right, guys. So, welcome to the first lecture here for the spring semester. We're going to talk about linear kinematics and reviewing the terminology sheet that I pass out. We're gonna spend some time and make sure that everybody knows everything. Now, the lectures themselves online are going to be very basic. I plan to use the time in class to go in depth and really draw that connection to the endurance performance aspect of class for these first four components. So we're going to take some time, go over some of the linear kinematic component, and then we'll talk about it. So for this outline, for this lecture, I'm just going to go over the math review. I'm not going to go much on that because you guys all said you pretty much know what you need to know. So I'll just give you the ideas of what you need to know. If you don't know them, you either need to come talk to me, or you just need to do some soul searching in Google search for yourself. We'll go over what reference systems are. We'll talk a little bit about position, um, velocity, acceleration, projectile motion, and running gait. Now that's a typo up there, position versus speed, but I don't feel like going back and changing it. But just know that it's just position right there. That speed would be down on the next level with velocity. But we'll go over that here in a second. So for the math review, um, terms that you really just need to know are scalar, vector. You'll see those come up here in a moment. Sine, cosine, tangent, and their inverse functions. So arc sine, arc cosine, arc tangent, and how to work back and forth in a triangle between those three and Pythagorean theorem. Now there are also instances that you may need to know the law of sine, law of cosine. Um, I don't know now how much we're going to get into the calculation of that concepts throughout class, but I'll know more of that. And then when those come up, if we need to go over that, we will. But I need to make sure that you guys know what a right triangle is and how to work with that. So if you don't know how to go back and forth, make sure you spend some time because it's a critical component of biomechanics is that you understand how to work with a triangle. So let's begin with just the reference systems. Now, the way we do our research in biomechanics is the reference systems are a key component to it. Um, they identify where everything is in relation to. Um, but I want to jump down to the global versus local this because this is a very important concept. The global is like your lab origin, right? So it's reference to the overall movement of a system of the body, say the center of mass. Um, if I put a lab origin in the corner of the room versus um, in the middle of the room to where I allow both positive and negative away from the origin, or is my lab space only going to be all positive? Those are key components, and generally in a lab setting, we orient it around something. So we usually do force platforms or some easy component that we can set up with a 3D motion capture. And then this local component. So local is more individual segments or joints within that global. There's also these smaller coordinate systems that we use on the system itself um, in relation to something else, right? So each of our segments, when we create a segment, they're going to have its own local origin or coordinate system. Generally, it's a 3D for what we do now. The 2D is X and Y, and that's what you take some normal video camera motion. But when we do 3D motion capture, we do an X, Y, and Z. Um, and it's important to understand that these axes or these planes are all oriented at right angles of each other. So now let's talk about what it actually means by linear kinematics. Well, so kinematics is just um, the identification of motion with relationship to a spatial and temporal component. So where they are in space and time. Most of your graphs you'll see will have the x-axis be the time or frame, depending on what the person chooses to use. There are instances where it'll be a percentage. We'll see that a lot when we talk about gait and stance phase and things like that. But the spatial component is where you get into position, displacement versus distance, those type of concepts. Um, Now the linear aspect is the motion that is either rectilinear or curvilinear. Now you'll see these two pictures on the bottom. The one on the left where it's all straight lines. You have A1 to A2, B1 to B2. That is rectilinear. The other one is a curvilinear. Now, it looks like it's a angular motion, but the important concept here is that all points along that A1, B1 move through the same space over the same time, so they all go through that same distance. Um, so that is the concept of linear kinematics. When dealing with the human body in sport movement, as you see with this picture, you'll see these markers on there, and that's what we use when we identify. This is a 2D image, um, but motion is generally referred to in a linear concept of those points through space and through time, right? So each one of those individual points can go through a linear motion um, throughout space and time. So that's what we would refer to from the human body. So now let's break it down a little bit further. So now we're going to go into each of the components that we use for the kinematic analysis, and we're going to start with position. Position is strictly where an object is in space. Um, it's defined as either distance or displacement, and there's a very distinct um, difference between the two, right? So distance is the amount of land or space covered. It simply means the total path traveled. And displacement is the shortest distance between your finishing point or the place where you end and your starting point, right? So it's often depicted as if somebody's going through a map and they go from around where the streets are versus the straight point A to point B, right? You often have to travel a longer distance to get to a point from point A to point B than the actual displacement. Um, this is actually one of the places that it's easiest to trim off during a race because what happens in a race time often, and I'm going to use the swim from Alcatraz to kind of be an example from this. But so these are both ideas from the swim from Alcatraz. Um, you can see on the one on the left, there's two individual routes. The ideal route is a straight, and then there's an individual who took more of a triangle route, and that's because of those arrows. The arrows are the current coming through. Um, it's difficult to maintain a straight line, right? So the white line represents that displacement. Red line is actual the distance that's covered. So the individual covers a lot more distance than they actually need to, or that's actually reported in time. And the same you can see on the right hand side. And this is the actual race from a GPS tracker. And they don't actually start from Alcatraz. This one actually, they start from a boat. Um, but so all think about all the races, right? So if you do an Ironman, the bike's 112, the swim's 2.4, and then you're running a marathon. But those are all marked distances that somebody goes around the path and marks it. Now, there are going to be spots along the race where you can cut corners a little bit, shave off time, but you always want to be towards the inside of the track because if you're the outside, then you're going to actually run more. Um, you don't want to cover a larger distance. You want to come as close to that actual race distance as possible, or even shave a little. Some of the best runners and best triathletes out there, cyclists actually shave some distance off their actual races, which is very very cool and very interesting to do legally. Let me make sure I make that a point legally. But you can shave some distance off in the overall race by following a correct path. Um, so now we're going to go into what is called the rate of change of position. Um, we're going to use the distance here. So this is the distance or the scalar component of rate of change. So when we talk about rate of change, you're talking about that denominator component where that's the change in time. So when we talk about speed, so speed is a scalar form or the scalar variable of rate of change of position, and it's related to distance. So it's that change in distance over the change in time. So that total distance covered over that time it took to cover that distance, right? So there you go. The path traveled, and then total time taken. It's a scalar quantity. Now, scalar means it's only magnitude. There's no directionality to it. So just think about the distance. It's not saying northwest, northeast. It's just saying that person traveled 2.4 miles. Okay. Now, rate of change of position for displacement, that's velocity. So this is going to be that change in um, position with the displacement P final minus P initial over that time it took, T final minus T initial. So this is that shortest distance on top, the numerator, minus how long it took. Now the units of both speed and velocity are the same. It's the unit of whatever distance measurements you have, displacement or distance, over the unit of time. So common for a biomechanical analysis is meters per second because we like to use the metric system. But one for us would be here in the States would be like miles per hour um, in your car. That is a form of rate change of position that we use. Now, to go for further, it's important. Acceleration only deals with velocity. There's not a continuation of the scalar form. So from distance to speed, it stops right there. Displacement to velocity continues on to acceleration. So now we're at the rate of change of velocity is acceleration. So that's the delta v over delta t, the final velocity or minus the initial velocity over the time it takes, right? So the delta t. Um, Now, it's very important here that you disconnect a positive and negative acceleration from directionality. So, with both position and velocity and speed, you are dealing with the origin, going back to that reference system, the global origin. A positive negative means either going away from or towards the origin. That is a very big meaning when you're dealing with those two components. When you get to acceleration, it doesn't have reference to the origin, and we'll see that more here in a second. Because look what it is. It's the velocity, the final velocity minus the final initial velocity. That is what it deals with. The velocity itself, not the origin of the motion or the reference system. So the units here is the unit of velocity um, with respect to another time. So it's meters per second or meters per second squared. So it'd be saying miles per hour or miles per hour squared. Um, so there's many ways you'll see it. You'll see it like I have it here, m per s per s. You'll also see it m times s to the negative 1 times s to the negative 1, or you'll just see it m over s squared. So those are all the different forms that you will see it. All are correct and all will be utilized for this class. So this is a little depiction that I hope will make it um, more apparent why the acceleration doesn't have a direction towards the origin. So let me describe what this is real quick. So you see the start and the finish there on the left. Now, what may be confusing, start and finish are the exact same point, okay? And we're going to make the start and the finish t0 or t naught and t sub 4, it's time 4, as the same point, okay? And that's the origin of this reference system, okay? So all the t's represent at point where they're taking a data collection, okay? So from t naught to t1, you're moving in a positive direction. So for this system, to the right of start and finish is positive. Okay. Now, they're moving right positive. It's an increasing positive velocity. What does that mean? Well, that means T1 is a higher velocity than T0. Okay. For this instance, it's probably T0 starts at 0, so that's an easy thing to do. Anything going the other direction, your velocity would be there. Now, that's a positive acceleration. That means that the V final at T1 is greater than T0. So it's a positive. Positive in the direction, positive difference. Now, going from T1 to T2, again, it's moving in the positive direction. But there's a decreasing positive velocity. What does that mean? Well, T2 is still positive, but its a magnitude is lower than T1. Let me say that again. T2, the velocity is still positive, but the magnitude is lower than t1. Okay, so it still has a positive velocity, but it is lower than t1. That means there was a negative acceleration. Okay, so it's going in the positive direction, but it was slowing down. This is that kind of concept that people mistaken a lot of times for just saying negative acceleration is deceleration, where that's not it. This is a case of it's decelerating. It is actually slowing down the velocity in the positive direction. Okay, now we're going to turn around and it's going to go back towards the origin from T2 now to T3. So this is going in the negative direction. It's increasing negative velocity. So whatever the velocity was at T2, T3 is the magnitude is greater, but it's also negative. Okay, so it's increasing in negative velocity. This is a negative acceleration. Okay, so it's increasing in the negative direction, the velocity. Now from T3 to T4, here's where it kind of gets a little tricky, right? And so this is where this shows you where that correlation does not happen with the acceleration and direction, because it's a negative direction, but it's a decreasing negative velocity. That means that T4 and T3 are both negative velocities, but T4 is a lower magnitude than T3. Okay, T4 still negative, but it's a lower magnitude than T3. What does that mean? Well, that means there's a positive acceleration. So if I take T4, think of the equation, T4 minus T3, if they're both negative, but T3 is greater, then my resulting equation would produce a positive velocity on top. Therefore, it's a positive acceleration. Okay, so that's where you get this non-directionality with acceleration. Hopefully that explains it. If not, remind me in class so we can go over this again. Okay. So now I want to get into concept and the importance of average versus instantaneous calculations. Okay, so average allows us to describe the general motion over a period of time. So what I've done here is this is going to be just a little data that is collected of the center of mass vertical oscillation. That's where there's going to be some small values here, but it's just a quick collection of points that will make things a little easier to understand, hopefully. But if we look at further, frame 3 and 1, that is actually 0.88 meters per second. Now, what does this actually tell us? So just to clarify things, the frames are snapshots, which you can see the times there. Each time change is a frame rate. So this is our normal data collection procedure. This is actually at like 128 point something frames per second because of some of the systems I use. Generally, it's about a 200, or if you're doing your normal camera, it's somewhere between 30 and 60 hertz, depending on what your camera is. But these are just quick shots, right? So this is a digital picture across the way. So what you can't find out, if I do the average between 2 and 1, I don't know what's happening and occurring in between 2 and 1, right? So this just says over that 0.008 seconds, something occurred, but the average velocity was 0.625 meters per second. Okay. Now, if I want to get more in depth, I can talk about the instantaneous. Now, this is going to identify the velocity at a specific frame. So I can identify the velocity at frame 2 when the frame is captured, or when the image is captured, or frame 3 or 5 or 6. I can't do 1 and I can't do 6 for this example because I need a frame before and I need a frame after. Okay. So tell me more importantly, what is occurring at that point. Now, when is it more important to find instantaneous over average velocities? Well, that's what I'm trying to identify, certain aspects of sport that the velocity is important, right? So they use this kind of information to determine how far a home run flies. that velocity of when the ball and the bat hit, and that initial takeoff velocity of the ball. This is all what they're using, this type of calculation. Also, you can determine the takeoff velocity of a long jumper, which coincides to how far a long jumper can jump. If you ever watch a long jumper, they're running as fast as they can and trying to hit at the perfect spot, right? So it's a very controlled, fast pace run. So these are all examples of when instantaneous velocity is more important than average because we're worried about that frame, that specific point, and what the velocity is at that point. So for that, it's whatever your ith point is. So for this example, P frame 3 in frame 1, that's going to give us frame 2. So if I want to know what your velocity is at frame 2, because say that is toe off, or say that is the point with the bat makes contact with the ball, I need the frame after and the frame before. And there it is, 0.688. Now I can do the same for 3. And I can continue on the line if I wanted to frame 5. Now I can go all the way to frame 5. So I've done 2, 3, and 4. If I wanted to do 5, I would continue the process and just do 6 minus 4 from both here. Now, one cool thing about this is the frame rate is, and what I don't have to do for every single time, the time of the after minus the time of the before, because I know that my delta t doesn't change. So it's 2 delta t the entire time. So this is just going to be another illustration of what we just talked about. So average, you're going to think about differentiation over a time period. In instantaneous, the method we're using is called the first central difference method. So A is going to be the average calculation. So you're looking in between frames, what is happening, but you don't actually see what's happening. You have the end and the prior. And then B is the first central difference method, where we're trying to identify the velocity at 5. So we're using then 4. So if 5 is the ith, then 6 is x ith plus 1, and 4 is x ith minus 1. Okay? And each of these has a delta t, so I can just do 2 delta t. Okay? Again, if we have questions on this, make sure that you ask me in class, because I want to clarify this, because this is going to be used quite a bit. It's going to be important that you understand how to use this if we start talking about how to calculate velocity and everything. So now I want to get into projectile motion, and I know you guys are all probably freaking out right now about projectile motion, but we're going to do it in the simplistic way. We're not going to spend a crazy amount of time on it, and I just want to draw it and understand why projectile motion can be important for endurance athletes, and where, from a research perspective, we look for projectile motion and what it means for us. But let's think about this again. Let's go back to instantaneous. And why is it important with projectile motion? And hopefully, if you haven't thought about it already, we're going to explain it to you here shortly. But think about it for another second. And think about your equations, think about what it is. And this should help you, but it goes back to these equations of constant acceleration. And we'll talk about what and why they're called constant acceleration in a second as well. But here you go. So here are these major equations that have probably caused a number of you stress last semester or whenever you took the class. But it's very simple. It's going to be plug and chug. It's identifying what it is. And I hopefully, in class, we're going to go over just a couple, because I want to make sure you can utilize these. But the instantaneous velocity becomes important because it's either the VI or the VF, right? So you're trying to find out one of those variables, the instantaneous component, when the person or the object becomes, or the system becomes, a projectile, right? So that VI is actually an instantaneous velocity. It's not an average velocity. You can't calculate this with an average velocity. You need to find out at that frame of release or that frame of toe off, what is that initial velocity. Okay, and that's going to be very important. Now, if you haven't seen it yet, there's an A in everything, right? And what is it? Well, A stands for acceleration. The equations of constant acceleration refer to, well, it's due to gravity, right? So gravity is a constant acceleration, negative 9.81 meters per second squared, or you can go to the metrics, the English version as well, but we only use the 9.81 because everything's going to be metric in our class. Um, but remember that these equations that we're referring to here only deal with the vertical, and that's why these are called the equations of constant acceleration. Gravity is a system that always accelerates. So whenever something is in the air in the vertical motion, it's accelerating due to gravity. Okay, it's always a negative 9.81, but remember when I go up, what's my velocity doing? It's slowing down. When I come down back towards the ground, I'm speeding up again. So keep in mind that the signage of gravity never changes. It's just the direction of motion of the thing may go. Okay. So anytime a system is in the air, it is acting. Gravity is acting upon it. Um, Now, the other motion, the other equation that deals with projectile motion is a horizontal motion. Now, if you go back to your book, there's a nice long equation, has cosine, sine, gravity, square root, all that good stuff in it. But we're going to make it very simplistic for you. Okay, so the initial horizontal velocity is main throughout if what? Well, I'm a biomechanist. I like things very simple. So what we're going to do with projectile motion, remember the entire projectile motion is we're removing air resistance. Okay. Now we're going to come up in this class, we're going to talk about things like cycling, which in swimming, where you're dealing with a lot of different air and molecule resistance, they call them fluid dynamics, that are going to cause motion to either decrease, typically decrease because of these motions. There is a time, especially in cycling, where you have a tailwind where it may aid in your velocity. But for this case, horizontal motion, we're going to talk about the initial horizontal velocity being constant throughout motion because we're removing air resistance. Okay, so here's your the range or the horizontal distance traveled is your initial velocity times your time. Now, again, notice the difference between this t and the t up in the equations of constant acceleration. The small t's are half t, the big T is total time. So the total time in the air, and remember the equations of constant acceleration only deal with half of a parabola at a time because you never know. The time up may be different than the time down. The distance up may be different than the distance down because you may be taking off from a platform or you may be golfing onto a platform. So these are all different things you have to take into account. Now, with this projectile motion concept, which of the three events of a triathlon do you think the individual becomes a projectile? So you have your swimming, your cycling, you have your running. At running, you were correct because running has a phase in there where the individual in the system becomes a projectile. Now, one of the things that I gave you guys on the sheet was some basic terms for um, gait parameters. Now, I'm just going to go over some running stuff. Now, this right here is actually a walking, but it's the same concept, everything. So you have on top your left heel, you have your left footprints, and on bottom right footprints. And this is going to just depict the difference between one step and one stride. Now, I will tell you that oftentimes people interchange the two incorrectly. They are not the same thing. Um, One step is from left heel to right heel or left toe to right toe. Okay, but it's the same distance or same point on the left that it is to the right, and vice versa, right heel to left heel. So the contralateral heel um, from one foot to the next. Different from stride, where stride is from right heel to right heel. So from right heel, it goes through swing phase, it comes down and strikes again. So the length of my stride is from the same foot hitting the same place, and you measure it consecutively, where step is from right to left or left to right. Okay, so that's a very strong depiction. Make sure you know those inside and out because it when I talk about stride rate versus step rate, those are two different things. Your step rate should always pretty close be double your stride rate. Your stride rate is going to be lower. So if you give me 180 for a stride rate, it's going to be incorrect. Okay. So this is just some 2D photographs, and this kind of depicts the frame, right? So frame one, frame two, frame three. There's 5 frames on top, 5 frames on bottom. The frames on top look like they're going to show you left stance phase, the followed by left toe off in frame 6, going all the way. So we'll talk a little bit about those right now. The aerial phase, which is 2 phases here. So a single gait cycle, so one running stride will have 2 aerial phases. Say that again. One gait stride, one running stride will have 2 aerial phases. So once my right toe comes off, I'll be aerial. My left foot hits the ground. That's one aerial phase. With left toe off, I go now aerial, and my right foot hits the ground. So there's 2 aerial phases. Okay, so this is when the runner is a projectile. So the only in the vertical, it is accelerating. So the only thing that causes him to be at its peak and go back towards the ground is what? It's gravity. Okay, so that's the acceleration. Is going up, slowing down, coming back down towards the ground is due to gravity. Okay, the horizontal velocity during this period of time, given that we've reduced air resistance, should maybe be maintained throughout. Okay. Now, this portion is called foot contact. Now, I constantly refer to foot contact. Now, there are different types of foot contact, and I don't like it when I read a paper or something and people constantly talk about heel strike because it's not always heel strike. Although the majority of runners are heel strike, not all runners are, and so we should refer to it what it is. It's foot contact. So that's any point of the foot connects to the ground. Now, typically, it's going to be the shoe first. Okay, so the shoe is going to contact the ground. Depending on the type of footwear or lack thereof, the foot would hit the ground eventually, but usually it's the shoe hitting the ground first. And it usually happens really small milliseconds prior to foot contact. But now it's important. This is where we get into heel strike, mid-foot strike, and forefoot strike. And there's a lot of debate, and this has become an area of great research over the last few decades. And there is some controversy on trying to make people shift between foot strike patterns if they're not injured. But we're going to talk about that more throughout the class. But these are your heel strike, midfoot, and forefoot strikes. We go back. So toe off is when the foot leaves the ground, and that is leading into the aerial phase. Now, the period of time from foot contact to the frame right before toe off, that's going to be your stance phase, and generally that is a important area for injury research. And then the last thing I want to talk about for this one is going to be the relationship of stride length and stride frequency. So again, look, I have stride length and stride frequency. So that's right to right or left to left. That's not right to left. Okay, so this is not step, this is stride. And what you're going to find here is running velocity on the x-axis. So going from left to right, you're increasing your running velocity meters per second. And on the right hand y-axis, you have stride length, and on the left hand, you have stride rate. Now, what you're going to find is at the slower velocities, as you increase velocity, you tend to increase your stride length first. And there's many theories behind this. Most people think that we identify more with the stride rate that is more optimal for us from a both metabolic and mechanical perspective. There's a lot of research out there to support this. I will tell you though that some current or recent research in our lab has shown that there is a difference between overground and treadmill running, and that on treadmill running people tend to alter their stride rate earlier, and you don't see that plateau that you see in stride length as much over outdoors. So there's some area for debate, and it's all about how people tend to analyze their data or record the data. And you'll see from this graph actually that if you look at the stride length up there, the very right for about 9 meters per second, there's quite a range. Standard deviation bars get pretty big. So there's a lot of variance on this, and this is a topic that we're going to go. But the most important thing about this slide is to understand that your running velocity is comprised of your stride length and stride rate. So running velocity equals stride length times stride rate, and that is something that you're going to need to know for this class. So following this presentation, the things that you should come out of is understanding what linear kinematics is, understand the position, velocity, acceleration, and a little bit of their relationship, how to move from one to the next, and know the average versus instantaneous components. You've been reintroduced to projectile motion and where in the running gait pattern you have projectile motion. So please come prepared to discuss, and let's have some questions, and we'll talk about, especially with this one, mostly with running, but we'll get into some of the other components too. But please come in with questions relating all this topic. Cheers.